presentation.
Yeah, you can start now.
All right. Thank you, Santosh sir. So, guys, today we have joined to understand fine-tuning in large language models. The agenda of this particular presentation is to give an idea, get a very beginner levels of eagle eye view of what is fine-tuning, how it is done in case of LLMs, and why is it needed. So, the main focus of this discussion will be to understand the limitations of the current language model or pre-trained models it has, why basically we need the fine tuning itself. Okay, moving forward. So the agenda here we'll be covering here, we'll be segregating our discussion into three parts. Why do we need fine tuning? What is basically the fine tuning itself and how it is done? And after that, we have a Q&A session as well. And also we have a working session where we'll be seeing fine tuning in action in our Google Colab notebook. So we'll hand out the notebook as well. In the agenda itself, while fine tuning, we'll be learning about the current limitations, what limitation does it has, and when to fine tune and when to prompt. I'll give you a complete overview about it. And in what is fine tuning, we'll get an idea about supervised fine tuning, instruction, RLHF, LoRa, QLoRa, and other techniques in fine tuning. And in how it is done, we'll be learning about how to create the data set, format the data set, how to train exactly, and what all the hyperparameters are, and all of this information we'll be learning. Okay, starting with why fine tuning. So the idea came into the picture. Why do we really want to fine tune? It all started with the transformer architecture, right? Transformer architecture, then again, as a probabilistic machine, it's just a neural network machine which intends to predict the next token itself. So pre-trained models predict the words. It does not understand your intent and all, right? So if you look into how the pre-trained models work, if you remember back at 2021 or when GPT-2 was released, they launched a playground where it was a more of an like a pre-trained transformer was more of a like a sentence completion. So if you ask it what is the weather today, or you just write the weather today is, you leave it there, it will sequentially complete all the tokens one by one. So it's more like a probabilistic machine which tends to complete the next word, predict the next word, what will be my next word, what will be my next word after that. And this is how a pre-trained transformer really works. The problem that we see in this pre-trained transformers are it is more like sentence completion. It doesn't understand the intent, what you are asking. It cannot give you the tone as well. Let's say if I'm asking, hey, if I'm in a formal tone or if I'm in an informal tone, it doesn't understand that. It just tries to predict the next token from its training data. That's it. Doesn't understand what the user is asking. If it is asking in a structured format, if the response should be, my response would be more formal or informal, or if I want to add any more insights to the user. Look, there is a huge leap between what we had in GPT-2 and now what we have in ChatGPT kind of a thing, right? If you ask it in ChatGPT these days, hey, what is the weather today? You'll see quite a good message, a preamble message there. Hey, Shahid, hello, and all of this information. And then it gives you a very structured information, right? All this was being done due to this supervised fine tuning or instruction fine tuning, say it. So we see that the limitation of pre-trained transformer is it's just a token prediction machine. It doesn't really understand the intent and the structure the user wants. So here you can see the example. If the user asks it to give me what fine tuning refers, hey, explain me the fine tuning casually, it just tends to complete the sentences next. It completely forgets if the user is asking in a formal, informal, if I should recreate something or something. And let's say if you ask list three benefits of fine tuning, instead of giving in more bullet points or something, a GPT-2 transformer architecture would have been predicting the next tokens only. So this is why the people understood that we need more of a fine-grained responses, more targeted responses instead of just completing the token. So here they came up with an idea, let's build something fine-tuning or supervised or instruction fine-tuning. Okay. Yeah. So Moving forward, we see two more gaps now. Since we understand that pre-trained transformer is unable to give us a targeted response, we see that the two gap arises very fastly. First is a task gap. If I ask a chat GPT, right, currently, hey, classify this, summarize this, what is my intent? What is the sentiment, right? It will give you in a single word. So currently it understand the question, user question, or user what does it really want to do, right? What the user is really asking. But earlier, in case of GPT-2 or some other pre-trained transformer, without any fine tune or instruction tune, it will just complete it. So there is a huge task gap. It doesn't understand what the user is asking for. What is the task the user is asking for? A pre-trained transformer or a not fine-tuned model. There is also a domain gap that you see. So let's a GPT or a pre-trained transformer, it always inherits from its training data. If the training data is more generalized enough, right? The blogs, the information that we see in the internet, over the internet, the data is completely filled with the generalized information. Let's say the people who are responsible for training the GPT or other models are picking the data from a more generalized perspective, right? They pick the data from internet, which is giving you the more general information. They don't have to tend to have a more specific targeted information about, let's say, legal domain, medical domain, or Indian culture or Indian civics domain, and all of this domain, right? So the model does not have the information about this specific domain as well. So a pre-trained transformers gives you more generalized information and not a very specific information until and unless it is trained on that data. So here we see that there is one more gap. It doesn't understand what task the user wants. It doesn't really have the domain knowledge as well. Also, there is one more problem with this pre-trained transformer is a knowledge cutoff problem. So let's say the model itself was training data is used up to 2023. Now we are in 2026. There is no more fine tune and the base model is ready without any data behind apart from 2023. After 2023 we say. So if we ask the question about something very more recent around 2022 or something, it will fail to answer. It will fail to answer it in a correct way. So it does not have the current knowledge. So it's then again an inherent problem. If I train it to a certain date, it will give information up to only certain date. Is also a limitation of a pre-trained model. Yeah. Based on this pre-trained information, right? Since we all say that GPT or any transformer or any language model is just a sentence completion or a token prediction model, right? Whatever you ask it, it always tends to complete your sentence. Even if it has the information or not, since it's a mathematical machine, right? You think of it as a model, it's a function. So whatever input you give, even if it's right or wrong or whatsoever it is, it doesn't really understand. It's just intent to spit the information, what it has seen from the training data. So this problem in the previous slide, what we saw is the knowledge cutoff problem and the hallucination problem, the domain gap problem comes inherent to this particular slide only. So it will, even if it doesn't have the domain information, it will still tend to complete the token itself, complete the next word. Even if it does not have the knowledge, very recent knowledge about something, it will still tend to complete with the wrong information. So there is a huge hallucination problem that we see in case of pre-trained NLP. So this so even if you ask it who won the Nobel Prize in Physics 25, it will just say put of any name from its training data. It will never give you the right answer until unless if it's trained on a such kind of a 2025 of a data and the model is trained up to 2023. So this is what the hallucination problems is. So all of this problem, given all of this problem that we are seeing here, we understand that it can be solved by a more robust way, that is through instruction fine-tuning or fine-tuning. Also, apart from this knowledge information and all of those inherent information, we also see the use cases of fine-tuning in the business as well. So let's say someone is a legal finance business kind of a thing, or BFSI domain or healthcare domain. They want very industry specific language model which understand the policies, documents, information about particular domain. So the business wants to do the domain specificity, can fine tune a model instead of going for a more generalized like a GPT or Gemini, this kind of model. They can fine tune a model based on their specific business needs. This will also improve the accuracy since we are reducing the hallucination problem. We say that, okay, it's since we are fine tuning the model on top of it, the accuracy will be more accurate. The accuracy will be more, and the hallucination what we see will be very less. Cost efficiency as well. So let's say if I want to do something very smaller task, and I just fine tune a very small language model for that. If I want to clean something data out of the model response or format data out of the model response, so paying for such a smaller task to OpenAI or other API keys will be much more costlier than pre-training fine-tuning an SLM and then doing all of these things. So it's also cost efficient sometimes, contingent that it has to be seen that all the calculation had to be done pre-hand. Also, the business is also keen to learn about the data privacy itself, since ChatGPT or other pre-trained general transformer models are heavily trained on the internet data. People also have a sense of getting their own data inside the premises and all. On-prem, they want to keep the data. So it also covers for the data privacy. If I have something more confidential or sensitive data about my company, I can fine tune that data and keep the models for me. Consistency as well. Okay. Now that we understand that all of those problems that we see can be solved via the fine tuning, now we really want to understand that what is fine tuning itself, how this models, the weights looks like, how exactly the fine tuning things works, what exactly the fine tuning is. Before going to this large language model fine tuning, it all, as said, we know that any LLM is again a neural network, right? So it is a combination of a transformer, new type of neural net architecture, that is a transformer architecture. But still, the basic baseline of it is a neural network. And then again, it follows the same pattern, how we train a neural network model, that is a gradient descent method. I don't want to be more technical over here, but I'll give you an overview how it really works in case of neural network. So let's say we have for any kind of training a neural network, we would need a supervised data to do it. In case of supervised, what really means that if the question is this should be my answer. If someone wants what is the sentiment of a sentence, given the sentence, this would be my answer. If it's right or wrong, or if it's heavily or something more targeted, outputs will be there. The labeled outputs will be there. So if say the task we are trying to fine tune or fine tune a neural network on top of a summarization task, then we should have on the left hand side we should have a long paragraph, and on the right hand side we should have the target small paragraph for it or summarized passage for it. Similarly, in case of when we say we are trying to fine tune a large language model, we really want it to give us a feel that, okay, it understands our question. It gives you a more structured targeted response, right? So when we say targeted response, we need to create the data which really holds the targeted response. And we start with the pre-trained model itself. We do back propagation with our own data, and then we adjust the weights. We calculate the delta weights. We add it, summarize it. We by the gradient descent method, we just upgrade the weights, and this is how, after upgrading the weights itself, we'll be getting our fine-tuned model. This is inherent from what we learned in our neural network classes and most of the machine learning classes we learned. Now, this is how a sample of instruction tuning dataset looks like. For any kind of a instruction data, mostly we have two kinds of variations of fine tuning. Either it should be a instruction fine tuning, or it should be a task specific fine tuning. So in order to complete the instruction fine tuning that we see here, this is the sample data should look like. Always it should have three fields to it. It should have the fields instruction, input, and output. So in the instruction itself, the user should have the question, Just a second. I think this data itself looks right to me. I'll show you one more different slide where it makes more sense. Yeah, here. So here, if you see the instruction tuning dataset look like this, an instruction, context or input that you can say, or an output. So whenever you ask, hey, suggest me some good restaurant, something to ChatGPT, right? And you gave that, you gave the context or input that, hey, suggest me some good restaurant at my nearby place, and my nearby place is something. So you give this extra context to it, right? In order to fill the gap for it. And then the chat GPT responds, okay, hey, thanks for asking. This is the best place. You said, I suggest this Italian restaurant or something. So this is how the output looks like. And then if you want to create a more targeted response towards the structure, right? I can show you this one, the slide here. For a task specific entities, you say extract the entities from this sentence. Now, if you give this to a pre-trained transformer without fine tuning, it will just complete the sentences. But if you create the data and train the data, fine tune the data in this structure, that whenever the user asks to extract the entities, this would be your output structure. The model will follow this procedure and always try to create the new responses in a structure output. So this is what our training dataset or instruction dataset look like. It always should have an instruction, an input, and an output for column for your reference. Okay, now moving forward, we know what exactly we are doing in fine tuning. We know that we are updating the weights. We know how the data should look like, an instruction input and output. Now we need to see what the model, the architecture or the layer inside the models exactly. What are the weight looks like what the really weight looks like, and what sort of weights we have, and what sort of layers do we have. So any kind of transformer architecture you look will have this layers itself. So let's say we are working with a Llama was a 7 or any Quen 2.5 billion model, right? So it will have 2.5 billion of parameters. Or let's say we are working with any 1 billion parameter model. So it will have 1 and followed by 9 zeros, individual numbers to adjust. So it will have this much of values inside it. And how do you know, calculate the value? So let's say we have a total parameter of this. This is our saper size. So we say that it's a 24 layers of architecture, 25 layers of architecture, and inside each transformer block. So let's say we say that Llama came up with a 24 transformer block of architecture. So each transformer block will have this of an architecture. Llama is just an example. It does not have to be true, but always it follows that it should have a Q projection weight, a K layer, a V attention layer. It would still have a MLP layer for sure, and other layers are layer norm, and other embedding layers are contingent to the architecture of a model. But for this overall, you'll always get this kind of an architecture, an attention layer and an MLP layer. So here you see, let's say if we have 1 billion of weights, the embedding token itself, it will get this 151. This is the dimension of my matrix. It will look this into this. So if you see a 3 by 3 matrix, it will have 9 numbers in it. If you see this matrix, it will have this into this. How much you will get the number? He will get that number of uh, parameters. Let me just multiply it. 151,936. 2048. So it will have around this much of parameters. It's too huge to calculate, something around 311 million something. So you see it in a single layer, it's that much of an parameters to update. In a self-attention layer, we'll have 2048 into 2048 number of weights to update. And in K layer, we'll have 256 into this. In V layer, we'll have that number of parameters. So in total, let's say we have 24 layers. So we'll have this architecture 24 times. Copied and pasted 24 more times. So this is how for each layer you'll have the model weights, and then after it, once you sum it up, it will result in a 1 billion only. Now, when we say fine tuning, we'll be updating this number of weights only. So while a batch completes, here we'll say, so this dots you see, this dots, this will be in a 1 million of a shape. right now. Will we, sorry, 1 billion. We'll have a 1 billion of dots here to update. This is how it is being calculated. And so you see the scale, how big of a model it is and how big of a task and tremendous task. So we understand that for in order to do such a huge task, we would need more resources. So fine tuning is not restricted or not exactly can be done in our single machine. It would need more compute and more resources in order to do fine tuning. So we now understand that why it really takes so much of effort and so much of resources to train, right? You see the numbers itself, and inside the layers itself, gradient descent is also a very huge tedious process to do. I mean, it's also a very computational process to do. So that's the reason, more reason to. Now we'll look what exactly full parameter fine tuning really looks like. So now that we know that how the layers are, so in our previous example, we have 24 layers itself. So when we have the training data, we'll just pass it through the neural network what we have, and then for each layers we'll have the updated weights during the full fine tuning. The training data will generate the loss gradients and then update the weight. So this procedure will continue up to the number of epochs or the number of steps that you have defined it. So let's say if the user is saying that I should update the weights on my training data for 60 times or 60 epochs, so it will run 60 more times. So for computing or updating 1 billion parameters across the layers simultaneously, you'll need a massive computer cost. So now we really understand that, okay, full fine tuning is something very huge, right? So there are two problems that we really see in full fine tuning. The first problem is the hardware cost and all. That could not be the first problem. The first problem, let's do it for the catastrophic forgetting. So here we see that it's kind of a total reset to the brain. So our brain itself has also a trillion of neurons, right? So let's say how a model works, our brain also has a trillions of nodes in it, also a trillion of parameters. So when you say, if I'm totally resetting my brain and I want my brain to learn the new information by full fine tuning, full parameter fine tuning we do, so it will forget whatever I've learned earlier, right? It will start forgetting it. So let's say earlier we had a knowledge of all of those knowledge, civics, economics, and all of this information, right? So those are our pre-trained information. During our childhood, during our 10th grade and all, we were pre-trained with multiple information. So we were just in a case of by 10th grade, we learned all of the information, what could be the possible knowledge that we can gather. So it's kind of a pre-training that we are doing here. After that, we are going into more specialized domain. Now we are into computer science domain. Someone will be into physics. Someone will be into management. Someone will be into that, right? So we are over the period of time, we are fine tuning our information with the information that we had earlier. So you also see a pattern, right? As we move forward to learn more about computer science, we tend to forget more about biology, what we learned in our 10th grade. We tend to forget more about the older stuff, right? So there is a pattern that we see is catastrophic forgetting also in case of large language models when we do full fine tuning. So earlier, if you had a translation model of English to French, it was able to do it. Now, since we have fully fine tuned it on a medical data, so it will tend to forget how exactly it should have a English to French kind of a translation. So this is one problem when we do a full parameter fine tuning. Also, given the scale that you understood right now, it's it's very hard to burn that amount of money and burn that amount of hardware cost. Also, it's very hard to get that amount of hardware, right? Nowadays, Nvidia and other chip makers like AMD has been coming up with this innovation and all to get more resource extensive, compute extensive hardware. But back in 2022 and back in 2021, it was completely restricted. It was very difficult to get those resources. So you see, fine tuning was very limited to the people who have wealth. But right now, it's more democratization and people were coming up with more innovations in fine tuning. So in order to fine tune a llama with 70 billion of full parameters, you'll need lot of memory, VRAMs and all. Training time will be huge, cost will be huge, and the storage itself will be huge. So one fact for you, GPT-4 was trained in 25,800 GPUs for over more than 90 days, actually, more than 100 days even. And the cost was completely racking up to $100 million to train a model of a scale with GPT-4. We understand that we use it daily. without any problem. We asked us a question, it gives you the answer in a very fast manner, and it does your job easy. But in the back end, all of this compute, all of this money has been burned to get you that. Okay, since we understand that full parameter fine tuning is so difficult, right? So it must be coming up in your mind, hey, why, if it's so difficult, why are people doing it? Why are people, everyone is talking about it, right? So they come up with a new idea. How do we really solve this full parameter fine tuning? Those challenges or not? They come up with an idea of parameter efficient fine tuning. The overall idea of this parameter efficient fine tuning is, so we have the information, we have the original model weights. Let's say we have a 1 billion of parameters what we had in our way, original model or base model, right? Now we don't really want to compute the gradient on the complete. Okay, if my screen sharing is turned off, right? Can you see my screen?
Yeah, it's fine.
Okay, thank you, Santosh. So I was telling you that in case of full parameter fine tuning, let's say if I have a 1 billions of parameters.
Actually, sorry. Actually, now it is turned off. Maybe you can try to share your screen again.
Okay.
Yeah, fine now.
Okay. Yeah. Thank you. So I was telling you that full parameter fine tuning, right? So we understand that if our model has a 1 billion of parameters and we are trying to fine tune it, so we'll be updating 1 billion weights in a single computer. We'll be doing it in a resource extensive manner where we'll be updating 1 billion parameters. But we came up with a parameter efficient fine tuning where you don't really, they came up with an idea, we don't really need to fine tune all of the weights of 1 billion. We don't really need that. What we really need is a tracking trainable parameters. We need to identify, okay, instead of 1 billion, I can come up with 1 million parameters. These are really important for me. These are the layers which I think that, okay, this could be the potential weights that I could train and track the upgrade in it. What should be my updated weights in it? Now we know the delta weights, right? I will not touch my 1 billion of parameter of model that will be saved somewhere. I don't really want to bother about it. I won't really harm it. That is stored somewhere else. I take the replica of that 1 million model and then I just update only a subset of the weights from that, and then I later merge it. There are different methodologies to merge, additive merge and all of this, but most of the people just add it by a simple scaling and add it. So here we came up with that idea. Instead of fully fine-tuning all of the 1 billion parameters, we should just look into a few subset of the parameters and track the delta change. We need to track for our data set, what should be my change in the weight? What should be my change in the weight? How should my, what should be the value that I should change in the weight to update according to my data set or my information? And then we later just add it. So this is what our parameter efficient fine tuning came up with an idea. Now, to understand parameter efficient fine tuning, we have a different methodologies to do parameter efficient fine tuning. And prominently, one of the idea is LoRa only, low rank adaptation. QLoRa is also there, but mostly there are all other methods, selective additive and all of those other methods that we see in parameter efficient fine tuning, but widely people use LoRa only. So I'll say you about what LoRa exactly does. I'll keep my focus towards the LoRa as it is the most prominent one. So let's understand how the LoRa really works. So this is going to be more technical and mathematical, but it's fine. I'll try to keep it as much as surface as possible to get an intuition and overview about what exactly it is. So before going to LoRa, low rank adaptation. So from the term itself, it says low rank adaptation, right? So we need to understand what really a rank is. We understand this weight itself, what we are talking about, this weights and all these are metrics, right? Huge metrics that we have. Okay, so I forgot to give you an information before going to it. Here you see information coming, right? If delta W, let's say if I was saying that, okay, I have a 1 billion of parameters in my pre-trained model, a base model, and I'm tracking the delta W of weights. And then again, you see the dimension of this delta W is again the same size of what I had, 1 billion of parameters. How does this really save our memory, right? There might be a question. It's of the same size. Even if in the image you can see earlier what we had, the same metric size we had in here. We just add it, right? So if we are computing all of those weights, how exactly it is saving our memory? People might come up with a question here. So here, to understand that, how exactly delta weights are being calculated, we need to understand what the rank is, what exactly the rank of a matrix really means. So I'll give you a very overview. The rank of any rank of a matrix really denotes how many columns or independent columns in a matrix really exist. So I'll give you an example here. So let's say it's a 3 cross 3 matrix, right? So the rank of the matrix either can be full, the rank of a matrix could be 3, or the rank of the matrix could be 2, or the rank of the matrix could be 1. Here, we're talking about 3 possible chances of the rank of a matrix. To find the rank of a matrix, we have different mathematical formulas, row echelon formula and other, but we don't want to go there. The idea of a rank is we need to find how many different independent columns that we can have. When we say independent, right? If how many, let's say 8, negative 5, and 7, is there any possibility I can use 8, negative 5, and 7 to recreate this other columns? No, right? These are, so we can say that these are three independent metrics or three independent columns that we see. I'll take you to one more example here. I'm just trying to find some easier example over here. If we can get I can create one matrix for you, but I can give you an overview what independent or dependent matrix would look like. So let's say one column would have a value of 1, 1, and 1, and the other column will have a value of 2, 2, and 2. The third column will have a value of 3, 3, and 3, right? So from the one column itself, if I just multiply 2 to the column 1, we can get the column 2. And if I just multiply 3 in my first column, I could get the third column, right? So it denotes what the dependency of a column really means, what really independent column means. So when we say column dependent column matrix, right? So it will have a three independent columns. We cannot use one column to recreate any other column. So that really means in a independent dimension. So let's say if we have a rank of 3, so it will have a 3 independent columns. We cannot recreate 2 more columns or 1 more column with any of the columns. And if it's the rank of a matrix is 1, so it means that using one column only, I can recreate the complete matrix, or I can recreate the complete other columns. I can scale it to the other columns. So now with that, understand what really a rank really means. So full rank matrix will have a 3 cross 3 learning channels, and a low rank matrix of a 1 will have only one independent column. So it's more like you get the intuition, right? So if you say a matrix is of around 3 cross 3 and I don't really want to have a 9 weights, I'll just break the matrix, factorize the matrix into 1 cross 3 here, a column matrix and a 1 row matrix, and if you multiply it, we can recreate the complete matrix as together. So it's like if the rank is 3, we'll have a 3 cross 1 matrix and a 1 cross 3 matrix. Here, if you see only 1, 2, 3, this. So we have 6 trainable parameters when compared to previous 9 parameters here. So it's a kind of a 33% reduction that we see here. Instead of training the 9 parameters earlier with a full rank, if I just introduce a rank that, okay, my matrix, I could decompose my matrix into a lower rank. I will just decompose into this one, factorize the matrix into this, and then I can get 6 parameters only. So I need to train x1, x2, x3, y1, y2, y3. So this is the idea of a rank. So rank is a matrix factorization method where you break your bigger matrix into two smaller sub-matrices. The method itself is called a rank decomposition. There are few ways to do it, but then again, okay. Moving forward, what exactly LoRa is? So here you see, get an idea what LoRa is. So let's say we have our original matrix of 1024 to 1024. It will have 1 million of trainable parameters, right? So if we fully fine tune it, we need to upgrade 1 million of parameters here. It's very expensive. But if you have a LoRa approach, you break this matrix into low rank of, let's say, 8. Here we are taking the rank as an 8. So I'll get a matrix of 1024 to 8 into 1024. I'll break the main matrix that you see here on the right to 1024 to 8. So it will have 8,000 and 8,000. So it will have total of 16,000 of trainable parameters. Earlier we had a 1 million. Now we have a 16,000 only. It's a kind of a 64 times of a reduction here that we are seeing. So we need to train this only. And again, exactly. So in order to training, the matrix A will have a initialization value of, I'll be more technical over here, but it has an initialization value. The weights are randomly initialized with a Gaussian distribution that we see over here. And the weight of B matrix will be initialized with 0 here. Now the rank were upgraded, the gradients are upgraded based on this initial parameters. So it will combine it. It will combine into it, give you the, now that we see the reduction of parameters, we'll train it, this A matrix and B matrix, we'll see the gradients, we'll upgrade the gradients, and then later we combine it to the frozen weights and we'll get an output model. So during the inference, here we see this A cross B will be in the same dimension what we had in frozen. So this W is frozen, our 1 billion model, we did not touch it. We just took a replica of it and we break the model, the matrix into two subparts. These are the trained weights. Now we just add it, and while during inference, we just give an input and we get an output here. So this is what a LoRa comes into the action. Okay, after LoRa, we see that there's a drastical difference in our weights, right? So the number of weights or trainable parameters that we see here. So right now we really understand that, okay, LoRa is a far more better option to train the model itself for a full fine tuning. Also, since we have a frozen weights, right? So we are just tracking it. Okay, earlier that, let's say we have a weight of 1.05, you just need to reduce 0.5. The delta W will be have a 0.5. You reduce that number and that's it. You'll be given a new knowledge here. Apart from after the fine tuning, for every a chat GPT, Claude, or any model, Gemini that you see, it follows 3-step procedure. First, you need to do a pre-training, what we saw. Pre-training will give you a sentence completion model or a base model. The idea of that model is to just predict the next token. And then we do instruction fine-tuning using LoRa or using full fine-tuning. People tend to use LoRa more over here these days. So it will give you how the model should respond in a structured way. If the user question is very friendly, then it's in a friendly way. If the user question belongs to a medical domain, then it should be in a medical domain. So this is the way you should do a supervised fine tuning and get the response. And after all of this, we have a RLHF phase as well, where the model outputs are more towards the alignment itself. Sometimes we see that ChatGPT restrained it from generating some of the harmful content, right? So this is the way this is the way it is being trained. So for an SFT model, could not be sometimes smart enough to contain itself. Sometimes we want that after fine tuning or instruction tuning, we want to restrain it from generating some other content that is good or bad or biased or, let's say, not allowed, something like that. We need to do an RLHF phase for it so that it should be more helpful, more honest, and it should be more harmless. And also for the bias reduction. Popular methods are there, DPO, PPO, and all other coming up with a new framework, but inherently it's again an RLHF only for reinforcement learning with the human feedback. So human will be here. We gave the thumbs up in ChatGPT as well, right? We often gives them feedback, right? If the response is generated is correct or not, if it is good or not, all of this feedback, right? So in the backend, they collect all of this feedback and then use it for training as an RLHF model, or train is for the RLHF procedure. Okay, so moving forward, now that we understand why do we really want to fine tune, what exactly it is fine tuning, now we'll be moving to the why, how do we really fine tune a model. So doing more practical over here makes sense instead of just talking. So I'll take you in only single slide over here about how the full pipeline looks like. And later we'll directly jump into the Collab notebook where we can see exactly how to fine tune a model. So this is the standard procedure we should follow while fine tuning any model. We just need to load a model. We need to have a weights, 1 billion parameter model of weights. If we are taking 1 billion model, then we need to have a pre-trained model itself. We need to prepare the data in the format that I show you, instruction, input, and output. We need to set the hyperparameters. What should be my R rank value? What should be my gradient accumulation step? What should be my number of epochs or steps? We need to define those parameters. And then we just simply train it. After training, we get the delta W, the new weights or the new optimized weights we get. Now we need to merge the weights with the the freezed model weights there. And then after it, we just simply do the inference. That's it. It's very simple on the papers, but in the backend, it's look complicated. But also due to some of the libraries like Unslog and all, it's very easy to fine tune as well. So let's go to the fine tuning notebook itself. Okay, so I've prepared one very small script here to give you an overview exactly how do we really fine tune. Here we need to wait for until unless this runtime gets connected. So thanks to all of this Unsloth, Axolotl library, Llama factory, so the people are, it's more accessible. Fine tuning is more accessible and easier. So they kept us with this libraries and all. They make our lives easier to fine tune. Okay, I'll explain you step by step and I'll run you through this one. So in order to fine tune all of this, we would need a runtime of GPU runtime for sure, so that we run the models and all. We would need Unsloth library, we would need bits and bytes, accelerate. All of these are libraries which is needed for running a LLM model, either inference or either fine tuning. So we'll just simply install these models. Okay, moving forward. So we have all of these numbers, right? Here we are trying to load this model, Quen 3.6 billion. So it has 600 million of weights, the nodes that we see earlier. And we are loading in at a 4-bit format. Then again, as we are saying that weights are a number, right? So the number we represent it can be in floating point 16, be floating point 32, or some precision, right? In terms of our human understand the precision as an integer, whole number, or decimal. In computer format, for decimal, we call them as a floating point. So when we say floating point 16, so those are decimal values with a 16 precision. It's more complicated than that, but for all overview understanding, you can say that, okay, it's a decimal value with a 16 precision. So here we are saying that it's a 4-bit precision value that we're taking. So our number will look like a decimal value with a 4 bits of precision here. So we are loading this model. It's a very small model. Just for the demonstration purpose, I've kept this model here. So here we are saying that max sequence length will be 2048. So our model will be able to produce 2048 of a 2048 tokens, or 2048 next tokens it will predict. That will be. We are loading in a 4-bit, since we say that, okay, it's a 4-bit quantized model. That's a separate topic of discussion. But here we are loading this model. It will take a couple of minutes to. Yeah. So you get all of these servers to see exactly what is happening. So we have a Tesla T4 GPU, free collab GPU. Number of GPUs is 1. What is our maximum memory size we can get? What platform it is using, and all of those verbose information you'll be getting. So here we are loading the model. It's of a 576 MBs of model. So we loaded it quickly. Okay. So now here we'll be getting the model as well. Here we are defining all of those hyperparameters that we really talked about, right? The rank itself here is 16. So we kept it 16. Either you keep it as 1, 2, 3, 4. You can keep it as any value. It's a hyperparameter. So the value should depend upon your empirical methods only. You need to find out what is my exact or sweet spot for a R. But ideally 16 is a train and tested number. People often keep it 16 for a initial level. But if you reduce the number to a very low, then you say that, okay, I'm factorizing my matrix. Let's say if I have a very big matrix and I'm just reducing it to a very small matrix, right? There is a chance of information loss. So we'll lose the information. And if we keep the R value very high, so that means that I have a very big matrix and I'm just creating one more big matrix towards it. I did not have a more reduction. So the VRAM will be, or the RAM it will be taking while training will be high. So there you need to find the sweet spot between the training constraint or the resource constraint and the information trade-off. You need to find the right R value. That's a hyperparameter here. And we are giving the target modules, which modules to look at. Since we saw that in our presentation, I'll just take it to you there. Yeah. So here you see we have a Q matrix, K matrix, and V matrix. All of these are our attention matrices. So attention layer matrices. So we are giving that, okay, you go and you find the delta weights. How should my this parameters or this layer should change? What will be the delta change for this layers only? And I'm giving them the target modules, which matrices to target. Q, K, V, and this gate proj, up proj, and down proj are MLP layers. Are our neural network layer. So this QKV attention layers will give us the information of get how to get acquainted with the new information that is coming. It's more like a how kind of a thing. How to give it, how to understand the user data that we are fine tuning with. And the gate up and down or MLP layers are like more like what to do or how after getting the information about how to understand the new data set using this attention layer, this MLP layers will give you what to update. Now that I understand how to do it, this layers gate up and down will tell me what to update, what numbers to update. So this is why we are targeting this module. Later, this modules, you can add any of the matrices that you want. You see the architecture of our base model and you can add it. But for the current moment, we are keeping it here. And LoRa alpha is something that we are saying that, okay, this is a scaling parameter. After it, we'll be scaling it, as we said, right? After we get the delta weights, we add it directly. Either we can add it directly with the base model, or we can scale it. We can scale, let's say delta weight, we can multiply it with a factor of 16 and then we add it. Here 16 doesn't really mean we are multiplying it 16. There is a formula that 16 by 16, it's like 1 only. 16 by scaling. So R and this will get cancelled out and we are scaling it to as number 1. So I won't go into the technical side of it, but that's what really means. And we have LoRa dropout. Dropout is 0. Bias is none, and you need to give other parameters as well. We need to do gradient checkpointing. So it's when we say checkpointing, it will, while calculating the back propagation or while calculating or updating the weights, it will save your checkpoints. It will save the numbers in your memory. That's it. Random state. This is as it is in machine learning we give, so that we are not getting different numbers every time. RS LoRa and LoRa config. So these are the numbers that we need to give. Okay, I'll also run this one. So here you see we have patched 28 layers. Instead here we have an example of 24 layers, but we have here example of 28 layers. We have 28 KQV layers. So this will have this layer itself will be multiplied or replicated 28 times, and we have 28 MLP layers, 28 zero layers and 28 MLP layers. So we're working at the 28 layer state. Okay, now that we have our from our information that we saw, how to fine tune, we have our model. Now we go for the preparing the data. Also, we configured with the hyperparameters. Now we'll go for the preparing the training data. So for every training data, you need to have a format, as we said, instruction, input, and output, right? And also a system prompt. Now that we see any kind of a GPT or chat GPT Claude model can come up with a system prompt. So this gives you more kind of a targeted response. So here we are giving it's kind of a preamble. We always give it. Below is an instruction that describes the task. This is how you should impersonate, and this is what you should do. Given the instruction, here is the input, fill the response. That's always the standard procedure of an alpaca format. Alpaca is nothing different. It's only an instruction, input and output. And also end of sentence token. For the model, the tokenizer comes, this tokenizer end of this token comes with the model itself. We need to find what it is and add it. And we create a function. It will take my examples. So let's say if this is my data, this is my instruction, my input, and this is my output. So I'll just iterate on top of all of this rows or samples. I'll just pick the instruction, I'll pick the input, I'll pick the output, and then I'll create one more column named text. And in the text itself, I will fill all of this. So here you see the format method, what it does. It takes the instruction, what we read here, it pastes it here. It take the input, it paste it here, and the output and paste it here. That's it. So it's the function is taking all of your instruction, input and output and pasting it here only. So we'll run this function, and this function. After it, my data is ready. So I've merged this. So here you see, this is my instruction. Input is empty. We can give it instruction input or not. And then this is my output. And here we have updated it. So here below is my instruction. This is my preamble. This is my question. Write a response. Give Give 3 tips for staying healthy. The input is empty. The response came up and pasted here. And the end of sentence token looks like this. So now we have formatted our data, all of it. Now we'll train it. So we use TRL library to train it. So Unsloth also uses TRL library. So TRL will give you the trainer method itself, class itself, object itself, and then you need to pass the model, pass the tokenizer, training data set, and what field it should tend to. It should tend to text field, since we have our data in text. And then you need to give the batch size, gradient accumulation, and warm-up steps, and all of this hyperparameter over here. Learning rate, what should be my learning rate? What should be my optimization method? What is my weight decay? LR scheduler type and all of it. I'll just run it and then we'll talk about it right now. Okay, so per device trained batch size is giving you how much batch or how much example should I take when doing the calculation. So it will take 2 examples while doing a forward calculation. So it will take these 2 examples and calculate the weights itself. And then it says gradient accumulation steps is 4. So I will do this same procedure 4 times. In the first time, I'll just do this and calculate the updated weight, and I'll save it in my memory. I'll do the procedure again same times with the 2 examples. I'll save it. I'll do it again in step 3 and save it. I'll do it again on step 4 and then I'll save it. After doing it this step 4 times, I'll just average it and do a back propagation or gradient upgradation after 4 steps. So this is what this parameter really means. Warm-up step is nothing but after taking the 5 training samples, or epochs is also here. I've kept it 1 only for the purpose. Just run this one. Yeah, number of epochs is how many epochs should it continue, or how many times the fine tuning should continue. Warm-up steps is then again it's a hyperparameter, which basically really means that after how many steps the learning rate should be towards the optimal learning rate or the example learning rates. It's a more technical. I'll give you an overview later. Maximum steps is 60 times. So it even after it's a 100 epoch, but we are cutting it off after 60 the steps, doing it 4 times and all. Logging steps is 1. After each step, it will log the loss. Optimization, we are using Adam optimizer, Adam W optimizer 8-bit. Weight decay is 0.1 and seed is 3407, what we earlier had. And we also pass the directory where we want to store our updated weights and all, checkpoints, weights, and those calculated gradient weights and all. Report 2 will give you the visualization. Either you can give track IO or 1B, weights and biases. So here you need to give the project path of your weights and biases. So all of those loss that we are seeing here will get logged into the weights and biases for later reviewing and checking. Now this is running for the 60 steps that we defined. So after each step, you see that it's taking, my gradient is going down and moving up. So as you see in Adam optimization, right? Sometimes loss will be high, low, and this way we are doing it. Okay, so it will run for 60 more seconds. It had 12 more steps in it. So for 10 more steps, yep. Eventually, if we do a lot of steps, it might overfit. So this is also a hyperparameter, how many steps we should give, how many gradient accumulation steps we should give, and all this should have to be empirical only. It cannot be either we need to find the traces from the fine-tuning data set and the base model. We need to combine the information. We need to do some trial and test. Empirically, at the end, we could find up with an optimal number. So all the numbers that we see here has been tested that this might be the potential optimal number. It comes up a default value, but for your particular task, we can play around with these numbers and have a good accuracy. Okay, after 60 steps, it's done. Now we use this model, we pass this model, since we have fine-tuned, we'll pass it into the inference phase. So here you can see this is my instruction, will be my input, and output the model will generate. So I'll just do this model.generate input. It will take my inputs as here. I'll give the max new tokens, how many tokens to generate, and all of this. I'll just run it. So if I take a question from the training data itself, you can see. So for the previous question, it is able to generate my responses. Here you see it has generated the Fibonacci series. And also I'll ask the question what we have in our training data, just to see how exactly it gives me the output. So the answer sounds like this: reduce energy consumption, use public transport carpool, be responsible with waste, and other steps. So let's see if this is the phrase we get in our responses. Several ways to reduce this one.
So Sahid, actually your screen got disconnected. Can you share again?
Okay, sure. Yeah, can you see my screen now?
Yes.
So this is the instruction that we copied from our training data, and this is the way it follows. The responses, there are several ways to reduce the air pollution. One of the most effective way, this, that, and all. This is how the training data also sounds like. If you see from our training, there are several ways to reduce pollution, including, look, exactly, it has not produced the same result, but it has the traces of our training data, our fine-tuned data. So here we can say that, okay, the model is using its own knowledge. Also, it has a traceability back to the training knowledge or the fine-tuning knowledge here. Now, I think that's it. The model has done the inference. You can do a pre-train and all. Yep. I think Sorry, I'm also going to. Okay, so these are some of the references that I use to collect information about. So these are the references, and any more questions, we are open to answer it.
Yeah, thanks, Sahid. Yeah, if you have any question for Sahid, you can feel free to ask.
Okay, if you don't have any questions, Santu sir.
Yeah, thanks. I think if no more question, yeah, maybe we can end the call here. Okay, thank you, Sahid. Yeah, if you have any question, later also people can contact you.
Yeah, okay. Thank you, everyone. We'll send it out, this PPT and with this collab notebook and all. So you can try it
Yeah,
out.
yeah, I suggest maybe you can put in a repo and share the link.
Yeah, I'll do it.
Okay, thanks, Sahid.
Thank you, everyone. Have a nice day. Bye-bye.
Thanks, Sid. Thanks, everyone.
Thanks, everyone.